Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, it's a great pleasure to have Professor Tong Zhang to give a talk today. Professor Zhang got a PhD from Stanford University, and before going to Rutgers University, he has worked at IBM Research and also Yahoo Research. Okay, today he's going to tell us about stochastic dual coordinate ascent.
Okay, thanks a lot. It's actually very nice to come here and talk about this because part of that is have some influence from people from this Microsoft, so we will see. One thing we want interested in is the problem of solving a very standard machine learning problem. It's a linear machine learning problem. Generally, you can write in this particular form, which have PW, which is usually we talk about primal problem with some loss function and some regularizer. So that's the problem we are interested in solving. Essentially, this is an optimization problem. And examples include the SVM, like logistic regression. So that's a very used a lot in the machine learning applications. Then you can also have some other loss functions like absolute loss or squared loss and so on. So one thing we will want to differentiate is the property of loss functions like SVM and the logistic regression and so on, Lipschitz, so-called Lipschitz, which is basically say derivative is bounded. The other one is smooth. Smooth means you have a second-order derivative. So there are two different type of properties we are looking at for these loss functions, and usually when you do the analysis, it turns out to be a little bit different. So for the loss functions, you can see some are smooth, some are Lipschitz, and some are both, and some are just one of that. So what we are interested in doing is solving this primal problem, which is a PW, which is a standard in the machine learning literature. Turns out there are the dual problems, so-called. You can define from this primal problem. Basically, given any primal problem, you can define dual problem. Essentially, for each phi, you can define the assume we are now assuming it's convex. So you can define the convex conjugate, which is phi star, and then you can write down so-called dual problem in this form. And the idea is they are related. So what the relationship? The relations are the follow. So first, you have a primal is P, W, and the dual is a slightly different formulation, which will be in terms of alpha and d alpha. Prime is always larger than dual. So that's the first property. The second property, which will be useful when you design algorithm, meaning that at the optimal solution, primal and dual are the same, and you have a relationship of primal and dual variable. So this one is a relationship, which means if I start to solve a dual problem of alpha, and then I can, at the whatever alpha, I can use this relationship to get a primal solution. Basically using the alpha to get you the candidate primal solution, and if you can solve a very good alpha dual solution, then we'll get a good primal solution. Another thing which I want to say is it's handy when you want to do the convergence analysis, convergence check. Typically, we are interested in how well you solve the primal problem, which is the right-hand side, primal suboptimality. You have a W, and there is best W. Of course, best W is unknown. So you cannot directly estimate the right-hand side, which you are interested in. But then if you are working with the primal dual formulation, because this weak duality, what you know is that the right-hand side, the primal suboptimality, can be estimated using the left-hand side, which you can observe. Because you just have any W and alpha, you can estimate the so-called duality gap. And if you want to say, I want to solve this problem to epsilon accuracy, I just want to look at the left-hand side with my W and alpha to say whether I can smaller than epsilon accuracy. So this is one thing which will be useful for this primal dual formulation. You can estimate the convergence directly. So this is one thing. Essentially, what we are interested in is there are two formulations. They are related by this form, and then you can estimate the convergence. So that's the. And here is an example. You can write that dual primal for arbitrary this kind of regularized loss problems. But the important one example is SVM, which a lot of people want to solve. You have a primal problem, which write in the primal formulation the first. And you have a dual formulation. You can write down. The detail is not important, but essentially you have a C kind of the relationship. And then you have this relationship, which is in the second. Essentially, you want to explore this structure to solve our goal still is solve the primal problem. But the idea is we want to do that on the dual. Because we already mentioned the primal dual have some equivalence. What you can do is try to solve the dual. I will find alpha to maximize my dual objective function. And I have a relationship because we know that this should be the relationship you are observing. And the dual coordinate descent is a very simple idea. At each iteration, you can optimize this dual objective function with a single coordinate. And you keep the rest coordinate intact. Essentially, you just update one coordinate at a time. And the important we also want a stochastic dual coordinate, which is one version of dual coordinate ascent, meaning that you want to pick the update coordinate alpha I, this kind of alpha I, randomly. And that turns out to be important. We will talk about that. Example of this one will be like here, the jump plat has this SMO. It's slightly different than this particular formulation because they have a constraints, but roughly using the dual updates. They probably not. Actually, I don't quite exactly know the details right. So but it's a kind of a dual in a dual. I think that's actually probably the one of the maybe the first algorithm to do dual, right? If in the machine learning, but you probably know more. But I would, from my understanding, probably. Okay, that's true. Yeah. Okay. So, but okay. Turns out that actually is important. We will talk about that later. But I believe SMO is probably first, well, at least one of the first. Try to do this. At least try to play with the dual optimization instead of primal. Oh, is that true? Oh, I didn't know. Okay, I thought it's random, so I might be mistaken there. The other one is a linear, which a lot of people use, implement this idea. But there are other people implement. I had my own implementation early on, probably a little bit later than SMO, but around the same time. But I will talk a little bit later about this idea. Oops. Okay. So here is just a comparison because a lot of people nowadays in the recent literature, people seem to forget about dual coordinate descent or ascent. They are more to do with online learning, stochastic gradient descent. So I want to make just some comparison just to see the difference. There are some difference, but SGD update rule, if you look at for this SVM, it's like there, and the highlighted part, the red part, is basically the computational intensive part. After the main computation is the inner product of your W and X. Dual coordinate is similar to main computation W and X. You can argue this one might be a little bit computational, but this can be pre-computed. So this one is not critical. You can pre-compute that. After that, this one and this one have the same complexity. and have a very similar update through in some sense. If you look at that, the update here, W, comes to there, and this W is somewhat similar. So I just want to give the association to say they are very similar complexity. Here is the result of you compare that. The earlier work actually is what they call Pasolsis or something, right? The SGD update, which is a pretty well-known SGD implementation of SVM. This is for relatively small lambda. Lambda is 10 to the minus 6. This for smooth loss maybe basically says I smooth SVM loss a little bit. So this is essentially the result of SGD, which is very typical. If you ever implement SGD, this is what you get. Turns out the stochastic dual coordinate ascent have this curve. So this is what we talk about random. It's kind of a linear convergence when you have a smooth loss. And here is a little bit variation of the stochastic gradient dual coordinate ascent. It's just instead of a complete choosing random, you play in epochs. Each epoch you random permutes your coordinates. So so essentially, but those are really linear, and they actually very. These are the epochs. These are epochs, right? So it's kind of, I would say, it's really shockingly fast when we first look at that. In the sense of, if you think about that in numerical optimization, lambda is very small in this case, 10 to the minus 6, which generally means condition number is very, very bad. And this kind of linear convergence is really, really fast when you think about a problem like this kind of yield conditional problem. So the question is how to explain that, which is essentially what I want to talk about. Basically, so why basically when you look at this graph, it's really quite. It's basically it's nothing like what you would expect from. Yeah. Oh, this one we okay. So in the current literature, people ignore this B thing. They ignore that. So essentially, you don't need to pick two updates. We are just picking one update. So SMO particularly pick two updates just maintain this dual constraints of sum equals 0, the constraints. So here we ignore that constraints. Yeah, and so we need one. So we didn't compare at all with SMO because of that. So this one is a simpler version. But I mean, in history, you should say SMO is one of these first. But right now, people look at the simple stuff. Yeah. Okay. This one is a smooth SVM. So we'll talk a little bit about basically you have an SVM, you smooth a little bit. You make the corner, they have a corner, right? SVM. You just make it smoother. Yeah. This is not 0-1 loss. This is all convex loss. 0-1 loss, this one you have to figure out something else. But oh, empirically. Oh, okay. Yeah, that's second issue. Right. 0-1 loss probably now doesn't make that much difference after few iterations. So here we are more interested in the optimization problem. Basically, how can you optimize this? But that's of course it's good if you're a practitioner. You want to say whether you need 10 to the minus 5th accuracy. You probably don't need that. Maybe you 10 to the minus 3 is enough. But if you even 10 to the minus 3 accuracy, this guy goes very, very long. So it just saturates. And the other one just shooting a few iterations. Less than 10 iterations, you get there. The other one is much longer. This is kind of like linear. We have our own implementation, but deep linear, as I mentioned, is kind of this type of stochastic. Yes. That's the important part. But I will talk about that later. Here is the true SVM. Basically, it's a non-smooth loss function. It's hinge loss, and you would see that slightly not quite linear, but still faster than SMO. Again, you want to understand this kind of convergence property. Still faster than the SGD here, right? So so we want to understand essentially why that's converged so fast. So that's one purpose of that. So let's look at the theoretical analysis, earlier one. So that's why it motivates what we want to do this. Of course, as I mentioned, we want to find something which is close to the primal optimal. Basically, we're interested in, say, after t iterations, my primal objective function is not worse than epsilon plus your optimal value. So roughly, the theoretical analysis is the following, the earlier ones. For the SGD, we can directly analyze the primal. And typically, the analysis is 1 over lambda epsilon. So that's the convergence after seeing so many examples. For stochastic dual coordinate ascent, there are analyses in the earlier ICM paper, which is basically a linear paper. They are following that with much earlier work of Luo and Sang. Essentially, it's kind of a linear, so that's something good about this. The problem of that analysis really is this guy can be arbitrarily small. When you see the SVM I showed you, it's actually become flatter and flatter. This is more actually asymptotic. Secondly, if you look at the proof, this one really depends on the smallest non-zero eigenvalue of your data matrix. That if you have a lot of data, it can be really arbitrarily slow to close to 0. So that's and there are some primal coordinate analysis you can apply to this scenario. They assume a different structure. Basically, for example, there are no lambda here, and this one actually has no lambda there. But essentially, they assume a different structure. They can apply to dual problem, but the resulting rate is not like that. It will be slower. And all this analysis also doesn't hold even for logistic regression, simply because they generally assume smoothness in the dual, and you cannot really assume smoothness or logistic regression in the dual because it's not smooth. So, yeah.
For the first one, sorry, I don't know how to pronounce this thing, mu can be after, so that's the smallest eigenvalue for the data.
Right. Okay. Actually, this one should be the inverse of that. Should be the, I think. Oh yeah. Right. This is the smallest eigenvalue of your XTX. Right.
Then this is not a problem, right?
It is a problem. Yeah. Because your dimension can be larger than your. Basically, the smallest eigenvalue can be very, very small. So there's no way you can control that. Yeah. Unless you have a very finite dimension, then it's a different story. But typically, we are looking at a huge dimensionality in the current situation, so it's not very good. And the other thing is, if I apply this kind of analysis only for dual, like this paper says, dual suboptimality. And turns out there's a gap. You have to be careful because we are interested in primal, so there are some issues there. What we really need is something like primal suboptimality or duality gap. Essentially, what we want to do is actually duality gap in this work. This one, I think I can skip a little. Basically, just say the following. You can just don't have to have the high-level message. Basically, say the following. There are problems with very small dual suboptimality, but very large primal suboptimality. So there are large. Essentially means when you do the dual analysis of dual suboptimality, it's good. It doesn't really guarantee you have a good primal solution. So there are situations like that. So you do not really. It's insufficient just to analyze dual suboptimality. So that's the message here. Basically, I just want to show our results. Essentially what we can prove. What we can prove is the following. For smooth loss, turns out it's a fast rate. Essentially, you have linear convergence rate when you have smooth loss, which includes a logistic regression with smooth SVM. For the hinge loss, which will be the Lipschitz but not smooth, you get slower convergence. This will be very similar to SGD. However, we know that the behavior actually faster than SGD when you see practical. So there's an explanation for that. In our analysis, basically, you can play around with the analysis to say, if the hinge loss, for example, is almost smooth, you can manipulate it to say I can have a faster convergence rate with something, but this something depends on your data. So essentially, which at least say why at least you should expect higher convergence rate, because you can turns out even though the worst case bound is similar to SGD, in practice when your data is good, then you have a faster convergence rate. So that's time a scenario what we are looking at. Essentially, this one explains why it's fast in the sense you do prove fast convergence rates. Now I want to compare this particular, because some people, if you just first see that, you will say, oh, then why don't you first just run SGD? We know it's slowed down. Afterwards, I will just run gradient descent, which we know have a linear convergence rate for this kind of problem. Turns out if you do that, you get convergence rate very different. If you do batch gradient descent, this is type of convergence rate you get. This is n times gamma lambda, n times 1 over gamma lambda. In our case, if you run directly stochastic dual coordinate ascent, you get a fast rate in the following sense. It's n times become n plus. And similarly, if you do this Lipschitz law, it's the same behavior. So what you really get out of this kind of, you are solving a deterministic problem, but what you really random trying to do this dual coordinate ascent is that you really have to take advantage of the property of a problem, in the sense you can significantly improve the batch convergence rate just by using this particular algorithm, making n times become n plus. So that's one thing. Just make sure it's actually very fast. And that's why you can see that very fast convergence rate. If you just do batch GD gradient descent, you will not be able to see that convergence. So the difference can be very significant if n is very large. Here is another thing I just want to mention. Our analysis only holds the stochastic dual coordinate ascent. Essentially, you have to randomize the sample. In my earlier implementation, which was wrong, is and a lot of people would think about that, just you randomize your order once, then you start using cyclic coordinate descent. Turns out that's a bad idea, because if you look at that, this is what you got. If you're starting to randomize once, this is smooth loss. You randomize once, you're starting to run your cyclic coordinate descent. This is essentially what you get. It's somewhat like the SGD. It's probably a little bit better, but not really much. So if you compare, they are comparable. And if you do the randomized version, you get these two curves. It's much sharper, sharper convergence. It's linear. This guy is not really, you cannot say this is linear. And this is our bound. So the red curve is our bound. Yeah. I do have, but then we can talk on the line. Actually, I do have intuition why this is the case. But from the proof, you can back engineering the intuition. But that's true. So but this one here, then it's just too much to. If you're interested, we can talk. Yeah, I can tell you why. But essentially, but this is a surprise. Although when we back engineer, we can find the explanation is actually somewhat surprising. So that's actually main reason why later a lot of people doing this dual thing for a long time, but then later they go to SGD. Just because I think most people just looking at this version, so not the other version. And the other thing I want to say here is randomization first is crucial, because you do see practical behavior. Second thing is if you look at again we want to say we're a little bit different than theirs, is that this guy's bound they are working with both cyclic and randomized. They don't tend to differentiate. But if you look at this bound, the only convergence they can get at best is like this, right? So this will be much worse than our bounds. Basically, let's say we do have a different bound. If you analyze cyclic, your theoretical bounds cannot be better than this rate. Yeah.
Just to make sure I understand here, so you have three lines, right? It's not just that the black line isn't good.
similar or related phenomenon is that the purple line is better than the blue one. So it seems that when you're fully random, it's not great. When you randomize only one time, it's not great. What you need to do is this permutation thing, which is kind of in between. And somehow that's magically better than everything.
This one you have, but right. Well, it's actually not necessarily. There's some other problem we can see. It's not. It's this one and this one. This one has, you can sometimes, yeah, usually you see a faster eventual rate for this one. But for the first few iterations, this could switch. For this particular example, this looks like that, but we will see another. The main thing about this, unfortunately, we cannot analyze that. So it will be interesting one to say what you can say about this one. So the only thing we analyze is this guy. But yes, so in practice, maybe you'll say there possibly have some analysis on this permutation thing. So right now, we don't know how to do that, basically. Right. Yes, yeah. That would, I think that will help, because what happens is for the blue thing, when you sample just you see a lot of iteration. Basically, if you just go in one pass, you don't see all the data. You really just ignore some data. You have to see a few passes to even see all the data. This guy guarantees you see all the data once you see all the paths. So indeed, if you intuitively will say this is probably a good idea, unfortunately, it's much harder to analyze, so we don't know how to analyze it. That one is one of these. Actually, I don't remember. I think Shai used it a lot. Yeah. Yeah. Could be, yeah, it could be. So for other data, they could be, but no. But also, it's depend on a lot of things. Depend on what the smooth loss, depend on lambda. So we will see actually the same data. There's slight difference later on, but we'll look at that. Here is you basically motivated by this. We know that at least smooth things is good, because when you have a smooth loss, we show it's a fast linear convergence rate. So therefore, maybe you really should smooth the loss. Even you work with SVM, you try to smooth the SVM. So instead, just to make a corner a little bit smoother. This is SVM, this is smoothing. And once you do that, hopefully you get a faster convergence, but it doesn't affect your classification much. Here it basically says classification. This is actually a very narrow region. Essentially, it says the classification is not, it's like third digits something. It's not really much affected, and you sometimes smooth better, sometimes not smooth is better. But here is convergence rate. If you smooth a little bit, this one is no smoothing. This is SVM. It's not linear. When you smooth a little bit, it's become more essentially asymptotically. You look at asymptotic here rate, it becomes faster. So this one is more like a linear. When you have this, when you smooth larger smooth. So it's really kind of more of a linear convergence, what you would get. So when you smooth, yeah.
So I'm wondering if in the SGD comparisons you can use the data before each epoch, because there's this ancient 20-year-old trick of the trade for neural networks of speeding training up by using the data for each epoch.
Oh, each epoch, really? Yeah. This one probably didn't. I thought that this one doesn't affect the SGD too much. It's more affecting of the. Right. Right. So it's basically similar to what we are talking about for the SDCA. That's we are not. I don't think this one is getting permuted, but that's a good point. Maybe I don't believe that will change much, simply because SGD does have the main problem is not the permutation. The main problem is the learning rate gets very, very small. So you really cannot do much anyway. You do have this kind of behavior. You cannot really get it linear. Yeah.
I think I have a follow-up question, or a related question. So you're saying that I think if I understand correctly, you're claiming that the dual coordinate descent, also in terms of the bounds, is faster than the stochastic gradient descent, but you're comparing upper bounds to upper bounds. And if you would have done this comparison, a year ago, they would have looked the same. But now that you've improved the bounds for one thing, it looks better. Could it be that the stochastic
You cannot, no, that you can have a lower bound. I think Lin knows much about, but there is no way you can do that linear. There's absolutely no way.
For the stochastic gradient method is the general method for solving stochastic problem. The lower bound is already matched to the algorithm.
Yeah.
Essentially, it's a randomized algorithm. But the lower bound that you have for stochastic gradient descent applies to the SVM type of problem. Something apply here. So we
Okay.
we're working on there is a randomized algorithm for solving a deterministic problem. That deterministic problem, if SVM, it should have the linear rate. But the difference is that if you explore random coordinate descent, the coefficient on the number. Yeah. So it's a deterministic problem and a stochastic problem. Their lower bound are different.
As basically HD you cannot, because actually one thing is the learning rate gets smaller and smaller. So there's no way you can really fix that, essentially. So unless you say I don't have small learning rate, but you get a lot of oscillation. Once you have a lot of oscillation, you cannot claim it's convergent either. So there's no way you can really do anything better.
So for this figure, you commute the example
for the stochastic coordinate ascent, yes, I think that also we do. But for the SGD, may not. I think Shai did that. I'm pretty sure it doesn't, but because that's typically people thought. Oh right, this one, yes. This one, yes, yeah. So when we compare with SGD, but this one, yes, all the stochastic basically says when you smooth, you get faster convergence, which is consistent with what we are seeing. The smoother, the faster convergence. So that's the message. And you basically, this motivates you. You want to maybe smooth your loss bound. That doesn't affect loss. Is like it's a 0, 1 or something. So yeah. Oh, this one you say doesn't change too much. It's a very small region. You look at it big, but this one, if you look at it, it's a small region, and it's unpredictable. This one, you can actually get a smaller error when you have a smoother. This one, you also get smaller, you have smoother. This one get a little bit larger error when you're smoother, but something here, you get smaller. So this says you can, there's no reason to not smooth. So that's the other one to say. The next one, y-axis. This is a loss. This basically say the primal suboptimality. Primal suboptimality. Yeah. No, there are different smoothness parameter. So. Right. Right, convergence. Yeah. They compared different by themselves. Basically, you change the problem, but the question is how fast you can solve that particular problem up to certain accuracy. Typically, 10 to the -5 would be really sufficient for machine learning. I don't believe anybody wants to go to 10 to the -10. It's more than enough, I would say, right? So. Mostly, I would say probably at this level is pretty good already. So yeah, at the 10 to -3. Yeah. There's additional relations. Well, turns out there's 2008 GMR paper. I think they have a NIPS paper earlier, maybe 2005, 2006. For smooth loss, they're similar, actually similar. So that one is, I think that paper still got cited a lot, but people didn't notice it's actually the rate when they compare. It's so good. So essentially, they have similar rates for the logistics problem, but they use a more complex algorithm. Turns out it's not necessary. They are more thinking about something else. There's a recent paper about this paper particularly, which got a similar rate by modifying the SGD. So they are also kind of, if you think about this, kind of a version of stochastic dual coordinate in some sense, because they are keeping the gradient. Keeping gradient essentially keeping the dual variable. So this one is a very recent paper. They got the same rate for the smooth loss. For the non-smooth loss, this guy, these are the same group of people. get something like using they have different motivations. They are again have something like basically all this solving on simplex. So they are thinking about exponential gradient has something to do with simplex. So they tried that. This guy I think Frank Wolf, for people don't know, it's kind of a gradient algorithm. It also can be applied for simplex. And they try to. Turns out this one boils down to be the same. They have different motivation. They get the same, and the bounds also the same as ours for the Lipschitz laws for the particular SVM case. You mean this one, right?
And so you have to generate a lot of random bits, and that costs computation.
I don't think it's more I don't believe so. I think they will be comparable. Yeah, it's comparable. Yeah, they have been random. If you tell me, although I haven't formally proved give an exact connection, I think this is a special case of dual coordinate in some way. But they are not writing in that way. But that's essentially what they are doing. That's my if you ask me, that's what my interpretation, and also the rate would be the same. So that's why, yeah. One thing I want to just give another little bit, just show you more intuition about these methods, dual coordinate ascent, because turns out it's the reason we are interested in that is it seems to be very fast rate. So let's look at again some comparison of this one with SGD. First compare bound, and then we'll look at some example. Bound is SGD convergence rate is this one. Stochastic convergence rate is this one. So if in some case, if your n is much larger, okay, so this one maybe not really say, essentially says one lambda is large, very large. You would expect the SGD to converge faster, at least in the first epoch, because somehow this one needs n. This guy doesn't need n, especially this larger means one lambda is large. One lambda small is not a problem. Turns out that's you can observe this question. The big question is just compare bounds, but we want to see whether the univerality it happens. This is where the univerality, when you compare SDCA with SGD, just focus on the first few iterations. One lambda is small, as we see here. This earlier version, this one I think is just for the SVM loss. So it's so you get this behavior. Basically, this one says SDCA dominance. But when lambda is large, as I mentioned, if you just look at the bounds, turns out SGD may be better initially. That's actually the case. So if you look at this guy, this is also the things where they cross. So originally we see this always dominate this guy, but here there are something slightly different. But again, the asymptotic rate is still faster. Here, I don't know about here. Maybe it's just up to the machine precision because they may just keep afloat. I think Shai did this. I didn't ask him here. Well, maybe some other reason. This one doesn't look right. You can ignore it, but essentially this looks like here. The first two iterations, indeed, the SVM is faster. So if you look at that, I think the stochastic dual catch up in the fourth iteration here. And that's consistent. So one idea is maybe you should combine that. At least when lambda is large, just combine these two to get a little bit better of both worlds. But this one, only when you have lambda is relatively large versus when your lambda is small, you still can just run the pure stochastic dual coordinate. Yeah. This one, okay. That's true, because this one lambda is fairly large. Yeah. So the convergence is fairly fast if you have a lot of data. Yes, that's true. I agree. So. So you have a lambda value that is between these two, then it seems that SGD itself is sort of very good enough at the beginning, and the accuracy at the beginning is already on the order of 10 to minus 3. That's true. So in this case, I agree. So that's why we can say combine. If you are lambda large, you have another option to say combine. Let's combine these two. Right, but in practice, maybe there's no need to That could be right. But typically, actually, the interesting is typically you want to use small lambda. So this scenario, the question is how interesting is this scenario, large lambda? But maybe it's somewhat interesting. But in many problems, you actually turns out want to use a small lambda for yeah. Yeah, this will explain next slide. But then yeah. Basically, if you look at the arbitrary rule, the things happens is this is the step size of SGD. It's a larger step size. This guy is a small step size. If lambda is very small, say it's at order of 1 over n, this one turns out to be good. Actually, it's more stable because you don't want the step size to be larger than 1 in some sense. And SD actually not that great in the sense of lambda t over n. It's very strange. When you have a lambda very small, you got a huge step size in beginning. At least the way at least those algorithms are written. Of course, you can say I modify a little bit, but still you get a huge step size. But when lambda is small, lambda is large, that doesn't happen. Essentially, this is a better step size because you are doing more aggressively, try to optimize your function. This one turns out is try to reserve that in the later round. So that's you don't see a lot of big. When n is very large, you don't see a lot of big progress early on. And essentially, what you can do is just change this to be t, and essentially, yeah, then you can modify that. Then basically, you get you can show something like this, make more progress early on, basically.
Like you change it to the minimum of t and n.
T. In the early round, when t is smaller than n, yes, you change that. Then of course you flatten that, right? Something like that. Then you get. So basically, here is the convergence you can get. You initialize with SGD by just changing that, yes, and then you do that. Basically, you run the SGD. Basically, you can SGD. I say you can use this version of SGD. You just change that to be t, and then you starting using the real stochastic then. You still do a little bit of manipulation, but the rate you got is this guy. So with the initialization, you got log n, which will be faster than this guy when it's log lambda. But actually, you can. I didn't show a graph, but you do see an improvement. So it will match SGD if you do that this way. But this is a rate you can got in our case versus when lambda is large, say 1 over square root n, you will have a change log n to log n, and you will see they are matching. But I didn't show that here in the plots. So I will talk a little bit about the extension of this dual coordinate ascent. The extension is the following. So originally, when people look at that, we use GW is two-norm regularization, basically W square. Here also I talk about x will be a vector. Here we are looking at a little bit more general framework. You want to have x are matrices, and G will be any strong convex function. So example of that will be you have multi-class logistic regression. So this will be your you can write this one in the matrix term in this case by multiple class logistic regression. Or structured SVM is another example. You can look at your regularization to say instead of L2 regularization like the standard, you're adding, for example, L1. So that's the generalization you can look at. The dual formulation turns out to be similar. You have primal. You can write down the dual. And you have a relationship of primal dual here. Instead of a summation, after summation, you take a gradient. So that's what you have. And this one, you can argue that as a generalization of the standard dual coordinate ascent by using this gradient here, basically. And this can be computed. Later on, we will say that. But here is the algorithm, basically. You look at this thing, and you have a dual. Again, we are interested in solving dual. Then you have this is a way you do some approximation. Instead of solving the dual itself, you try to approximate this part of the dual, basically G, the regularizer. You want to keep the loss function dual the same, but you want to do an upper bound of your dual of your, you just do an expansion by this strong convexity assumption, you go upper bound. This one can be efficiently solved. The point why we want to do that is that the original one, when you do the update of delta alpha, is not efficient. But once you do this approximation, you can do an efficient update of alpha, just like what we see before for the SVM or SGD and so on. So the key is you want to do this approximation. Once you do that, you just, again, run the randomly pick I. Then instead of solving the dual, you're solving this, this version of dual, just the approximation of dual each time. You just update approximation. So the idea is make it easier to solve. Update the rule simple. So that's the main idea here, trying to use the upper bound of G instead of G itself. Example, you can work out for the L1, L1, L2. This is logistic. You don't need to care about this part. This is logistic, but the main thing is when you work out that one, you have a typical truncation step, which essentially shrink your soft, also called soft thresholding. You have you are shrinking your each observation towards 0. Minus something, 0, and up something. This is, if you're familiar with the literature, you see a lot of this kind of thresholding in L1 related, but essentially that's a typical shrinkage people apply. Here, when you write down the dual, this will be the form you would get. And basically, you keep up V and W with the truncation of V with certain parameters. And here is the algorithm. Basically, this is essentially the algorithm you would solve. The main point I was writing here, again, similar to earlier, you have a truncation of V times W. This was the computation more complexity part. Xi square, again, this one, you just need this two. The highlight part is the most computationally intensive part. The other part are the one-dimensional problem, which is simple to solve. Here, and this one, again, you can pre-compute. So the key part is really the computation is solving, compute this one. So that's the most computation intensive part for each step. And this one, I would just say, very similar to Lin's work, dual averaging. The dual averaging and compare with this is like comparing SGD versus the SDCA. Basically, this one is very much the this one extended to the SGD. Here is the extension to the dual coordinate ascent. So that's the analogy. If we look at the convergence rate for the for this version, turns out the analysis could be done exactly the same way. You get the smooth loss function. You get this kind of convergence for your smooth loss, and you get Lipschitz loss. You get this one. And you can also say the same argument to say if it's asymptotically almost smooth function, you get faster than this one. So here is for solving L1 with smooth loss. If you have a smooth loss function, you want to solve L1. If you apply this particular formulation, you can choose lambda is O epsilon to get epsilon accuracy. And this is the computational iterations needed. And of course, you can apply dual averaging. For the SDD version, it will get this computational complexity. And you can apply batch algorithm. This is a state-of-the-art algorithm. So batch algorithm will be this complexity. It will be n divided. The reason they have a square root of epsilon will be because they are using a nest of acceleration methods. Then you can get n over square root epsilon. If you compare this rebound for the interesting case, which will be the epsilon not too small, if extremely small, then this will be the fastest. But if it's not so small, it's 1 over n squared, which generally will be okay for the machine learning applications, because machine learning, you don't really need to be smaller than 1 over n in some sense. So in this situation, this one will be faster than this guy. This one also faster than this one. So again, the convergence is better. So I think I could go a little bit about, but I'll quickly just say you don't need to look at that. So the main idea about this proof is actually the key lemma or simple lemma. It's not really hard to prove. I think it's just 1 page or a little bit more than 1 page. You can prove that. But the key observation actually is the dual improvement can be bounded by using the duality gap. This is duality gap. Basically, say if duality gap is large, then you have to make a big improvement for the dual step. That's the key idea. And if you apply the different laws, you get this one particular laws for the smooth laws. This term vanishes. Basically, this is where you can use to get linear convergence. Basically, you apply this lemma. Essentially, says dual. Each time the improvement of dual will be not too small if if this guy is large. It's basically duality gap is large, and then you can, because duality gap is larger than the dual suboptimality. Basically, you can prove linear convergence rate of a dual. Once you prove a linear convergence of a dual, this automatically implies linear convergence rate of the duality gap because of this inequality. So essentially, the idea is the key observation is really the duality gap improvement when you do the dual coordinate ascent. It has to be randomized because everything is taken in expectation. If you don't randomize this, this actually doesn't hold. Complete breaks. Then I don't see any way you can modify this proof to deal with non-randomized situation. So that's why this rate, if you look at this cyclic version, it's not very good. But essentially, that's the idea. So the summary, of course, if you're really interested, you have to look at the paper. But the summary is this one actually works pretty well. And it's being forgotten. One reason, of course, is a lot of people early on played around with the cyclic version, not the stochastic version. And so people move to SDD because they are kind of similar in some sense. And the one thing important, of course, we have analysis, but important is you really have to use the stochastic version, randomized version. And the previous analysis not very satisfactory. Our analysis says once you do the stochastic version, it's really you can get very fast convergence, especially for the smooth laws. The other thing is you can generalize this proximal generalization. Turns out even the analysis is very analogous in some way to the dual averaging. The main difference here, I think there are some you repeat use alpha. You have to, and but you can do that like a dual averaging. You can extend this one to the proximal version. You can handle more complex regularization problem like L1 or some other problems. And essentially, you get the same performance with the standard version. And if you compare the rate, you have a better than traditional methods in the interesting setting, like a statistically meaningful setting. So then that turns out to be a very good choice. Okay,
I
yeah.
have a question. So, I mean, I think that many practitioners became frustrated with stochastic gradient descent because exactly the graphs that you were showing.
Yeah.
And what they did is they moved to the quasi-Newton type of updates.
But like a John, right?
Back to this, or I mean, do you have any idea of how they compare?
So I talked with John. So I think this one, Alec and John, right? So this guy promote that. Of course, the rate you can get for quasi-Newton will not be as good. So that's for a theoretical issue. For practical issue, they are worried about the randomization. So they don't like the randomization. So if you want to really do distributed system, large scale, there are still rooms to see what is the best way. Maybe you don't really need full randomization and other things, but we haven't really tried experiments a lot. But let's say if you don't worry about randomization, I probably would say this might be better than the quasi-Newton stuff.
You're saying if randomization were free, then this would be better. But because randomization makes
potential. I don't know if it will make, but they are worried about that. Yeah, and yeah, then you have to do some research to figure out. Yeah. Okay. Okay.